When we ask why the stars are silent, most answers reach for the exotic. Alien AIs, great filters, or civilizations too advanced to care about us. But maybe the reason is much simpler. Maybe they just ran out of gas. When it comes to figuring out why we don't seem to see any aliens in a universe so vast and ancient, the answers usually fall into three broad camps. First, that intelligent life is rare for some reason. Second, that it is not rare, but is simply hard for us to see or hear. And third, that neither is true, that intelligent life is common, and some is even visiting Earth. There's no strong consensus or evidence locking into any one of these particular possibilities, but rarity tends to lead the pack, and the various reasons for that usually fall into what we call filters, things that thin out the number of civilizations along the path from being a microbe to someone who builds microscopes to study microbes. That perspective is a humbling one. We are, after all, descended from those same microbes, which remain the dominant form of life on Earth, and yet we, the most intelligent species our world has ever produced, spent most of our history unaware that microbes even existed. That's a useful bit of humility to bring to any discussion of the Fermi Paradox, the great question of why, in a universe so immense, we seem to be so immensely alone. And since today's topic is fossil fuels, I should note right away that while we often joke that coal and oil are made from dead dinosaurs, they are actually made mostly from much smaller organisms, microbes and algae. That detail will matter later. Most filters we discuss in the Fermi Paradox deal with the early stages, the long climb up from single cells to tool users. But there's another category, the late filters, which apply to civilizations like ours, the ones already here but not yet out there. To be the kind of alien we ourselves could detect, one with a homeworld hundreds of light years away, we still have a few major hurdles left to clear. Today we are looking at a filter, actually a handful of loosely related filters, the fossil fuel filters, that propose that civilizations like ours depend on a geological lottery, the lucky accumulation of dead plants and microbes cooked into coal, oil, and gas. Without those, there's no industrial revolution, no rapid growth, no easy metallurgy, and no launch pads to the stars. And even if a species wins that lottery, it might not last. Burn through your carbon too quickly, collapse, rebuild, and repeat, and each cycle leaves you with fewer easy seams to mine and less surplus energy to recover. Eventually you hit the final dry well, the last coal vein, and your civilization fades back into pre-industrial quiet. If that idea is true, the Great Silence might not be a cosmic mystery, just the sound of a universe full of worlds that never found or lost too soon their first fire. There's a few different parts of this theory and a few angles, and we'll explore their reasoning and then their strengths and weaknesses, as we usually do. As usual, we'll be here for a bit, so a drink and a snack might be in order. Possibly an awesome SFIA coffee mug. Fossil fuels may be what run our civilization at the moment, but coffee is what runs SFIA, and don't forget to like and subscribe to the channel. The fossil fuel hypothesis. Let's start by giving the argument its best form. On Earth, fossil fuels were the scaffolding of everything that followed. They provided compact, storable, transportable energy, the first power source that could be burned anywhere, day or night, to run engines, smelt metals, and power chemical industries. Coal gave us iron and steel through coke furnaces, oil gave us mobility and chemicals, natural gas fed fertilizers and plastics. Together they powered this feedback loop that became the Industrial Revolution. So the logic runs like this. 1. To build advanced technology, you need a large, constant energy surplus. 2. To create that surplus, you need fuels with high energy density that can be harvested and stored easily. 3. On Earth, only fossil fuels met those conditions before nuclear renewables existed. Therefore, if other worlds don't have them, they may never climb that same ladder. And again, a harsher variant says even having them is not enough. Fossil fuels are finite, and if a civilization squanders them before developing alternatives, it is finished. Or at least is finished for the millions of years it would take to regenerate that supply. Some would probably be left over, but each collapse depletes the easy reserves that powered the last ascent. After a few failed attempts, the species may have the knowledge but not the means to rebuild its industry, a fossil fuel death spiral. From that viewpoint, the universe could be full of brilliant but stranded worlds, planets where intelligence arose, burned briefly with coal and oil, then dimmed forever, civilizations too tired to rise again, too cold to reach orbit, and too quiet for the neighbors to hear. It is an elegant and melancholy vision, and one that might even sound plausible if you assume that fossil fuels were our only road to the stars. Next, we'll look at whether that assumption holds up. Fire without fossils. Of course, before we start mourning for all the hypothetical civilizations that never struck oil, it is worth remembering that we didn't exactly wait for gasoline to be invented before learning how to burn things. Of course, I was just reading that it occurred to me that pyromania might be a necessary trait for any civilizations wishing to ascend the technological ladder. Maybe that needs its own episode too. Humanity's first fuel was not fossils, it was wood. Firewood, charcoal, and peat kept us warm, cooked our food, and powered blacksmiths long before a drop of crude oil ever saw daylight. And ethanol, good old-fashioned grain alcohol, predates gasoline by millennia. People were distilling fuel long before the first refinery, mostly to get wasted, and in principle, you can run an engine on wood gas, ethanol, or almost anything that burns hot and clean enough. Methane and natural gas, too, are almost certainly common across the cosmos. They form easily from simple chemistry and show up in the atmospheres of planets and moons all over our solar system, from Titan's methane lakes to Neptune's deep blue storms. Any world with active geology or decaying organics is likely to have some form of it. Even without dinosaurs or forests or algae mats, there are plenty of ways to get flammable gases. And while it's true that only an oxygen-rich atmosphere lets you burn those fuels efficiently, that itself is kind of an interesting Fermi Paradox twist, a kind of biofilter. You need life not only to make fuel, but also to make it burn. Oxygen in the atmosphere was a late comer, long after life emerged and was quite robust. Worlds with more active geology might never come to be saturated with oxygen in the upper layers of Earth and get an oxygen-rich atmosphere as a result. And so too, they might be too geologically unstable for any deposits of coal or oil not to get broken up. Something most folks don't realize is that the vast majority of oil seeped out over the eons. Worlds with less earthquakes and slower geological turnover might have much richer deposits, or catch on fire easier as they might have higher oxygen ratios than us. A world full of methane and hydrogen but with no oxygen would have all the ingredients for fire, a cosmic chemistry set forever sealed inside its box. So perhaps our good fortune isn't that we had coal seams and oil wells, but that we had the air that made them useful. There's obviously also the concern of runaway greenhouse effects from CO2. The evidence seems to tilt away from that being likely on Earth, but not every planet is Earth, and some may be more or less susceptible to it. We still don't really know, and probably shouldn't find out the hard way. That industrialization itself inevitably kills off your civilization is a fairly common Fermi Paradox late filter, and this would fall into that realm. There's also the question of the linger or dwell time of CO2 in the atmosphere, and models vary, but carbon dioxide drops off quicker initially. Most that I've seen support carbon dioxide dropping by about half of its increase in a few decades, with most of the remainder gone in a few centuries, though a full return to normal might take many thousands or even tens of thousands of years, and you would have permanent ecological effects such as extinction that might, if severe enough, take longer to fully repopulate the new or returning ecological niches. In geological timelines, that's not really a bar to civilization restoring itself fairly quickly, even if it had collapsed from that, or somebody like chimps or smart raccoons replacing us in a million years. As for those who fear that civilization might blow themselves up and rebuild and do it over and over until they run out, and fall into some eternal apocalyptic dark age, it's worth noting that only civilizations advanced enough to build nuclear weapons can create that problem in the first place. And unlike fusion, where making bombs turn out to be easier than making power plants, fission works the other way around. A reactor is much simpler than a warhead. If you can destroy your world, you can almost certainly power it too. And a modified version of this theory will generally suggest we could run out of uranium too, which is viable, but needs to be kept in mind that uranium-238 is vastly more abundant than uranium-235, and can be made into a fuel in breeder reactors, and that thorium works too. I should also note that there are ways to produce neutrons or alpha particles that do not actually involve using uranium or thorium. So not an unlimited source either, but you would need very many cycles or very long periods of usage for this to work, and I tend to be dubious about repeating cycles hundreds of times, or that a civilization lasted long enough without blowing itself up to use up all its fossil fuels and fissile fuels, and did not manage to get better energy options while that was the case. So before we start assuming the stars are quiet because nobody had gasoline, we might want to remember fire itself is not rare. What fossil fuels actually gave us. It's easy to dismiss fossil fuels as dirty relics now that we have cleaner power sources on the horizon, but we shouldn't forget what they gave us. For nearly 2 centuries, they were the spark that lit the modern world. Coal, oil, and gas offered something no other energy source had before: concentrated, storable, and portable power. A barrel of oil or a ton of coal was, in effect, a box full of sunlight that could be burned anywhere, day or night. It was energy on demand, not tied to rivers, weathers, or seasons. Their convenience reshaped civilization. Fossil fuels didn't just power machines, they powered feedback loops. Cheap heat produced cheap metals, which produced better engines, which dug more mines, which made more power. The Industrial Revolution wasn't a single invention, it was an accelerating cycle of abundance. That's why the fossil fuel filter idea resonates. It's not just these fuels were useful, it's that they were easy. They burned right out of the ground. You didn't need massive infrastructure or intricate knowledge of electromagnetism to make them work. Just a shovel, a match, and a little ambition. And that ease made it possible for small, fragmented societies to leap into industrialization long before they were ready for large-scale coordination. Coal mines came before power grids, steam engines before turbines. We learned as we burned. So yes, fossil fuels mattered enormously, but what they gave us was not a singular miracle. It was a shortcut, a quick start to let us race ahead faster than we could walk steadily. Civilizations under the wars might not find that same shortcut, but does not mean they can't reach the same destination. It just means their climb might be slower, steadier, and perhaps a lot less smoky. Geological reality check. The fossil fuel filter sounds compelling at first, the idea that civilizations might rise and fall depending on whether their world ever formed coal seams or oil fields. But geology, like life, tends to find a way. And when we look closer, it is hard to imagine a truly barren universe in this regard. Carbon is one of the most abundant elements in the cosmos. It's forged in the hearts of stars and scattered across every planet that forms from their ashes. Hydrogen is even more common, and when those two meet under the right pressures and temperatures, hydrocarbons appear almost automatically. We've seen them on Titan, Neptune, Pluto, comets, asteroids, and even the atmospheres of exoplanets. The universe, it seems, is naturally greasy. On Earth, our fossil fuels came from ancient life, but they do not have to. Methane, ethane, propane, and the heavy oils can all form abiotically, deep in planetary crusts or mantles. All that's required are carbon-bearing minerals, hydrogen-rich fluids, and a bit of geothermal heat. So even if a world never knew biology at all, it might still have natural gas. And if it does have biology, the odds only improve. Microbial mats, algae blooms, and buried organics are efficient at trapping carbon and hydrogen together, baking them into the planet's crust over eons. What's rarer than the fuel is the oxygen to burn it. For most of Earth's history, our atmosphere could not have supported a candle, let alone an industrial revolution. It took billions of years for photosynthesis to fill the sky with enough oxygen to make combustion practical. So while hydrocarbons are nearly universal, the ability to use them depends on life already transforming its planets. That's an odd inversion. The very thing that makes fire possible is also the product of life itself. In that sense, oxygen-rich worlds are their own kind of Fermi filter, a place where life not only exists, but has already had the audacity to change its atmosphere. Even so, not all fire needs oxygen. Hydrogen and methane burn cleanly in chlorine or in fluorine atmospheres. Metal dust can combust in sulfur vapors. Chemistry allows more possibilities than our earthly biases imagine. A world's fuel might not look like oil, might be liquid ammonia, metallic hydrogen, or even exotic oxides that was born in volcanic mist. And we've looked at life based on those alternate chemistries in recent years too. In fact, we just released a compilation episode of those along with some new ideas. And once a civilization understands chemistry, the need for fossils fades quickly. Synthetic fuels can be made from carbon dioxide, hydrogen, and water. Energy is the key input, not coal seams. It takes more energy to make fuel than you get by burning it, but given its easy portability, carbon-neutral hydrocarbon fuel made from surplus solar power is entirely plausible and very viable if you run out of the pre-made ones. Whether that power comes from wind, sunlight, tides, or nuclear decay does not matter much. The universe provides plenty of ways to run an engine or charge a battery, albeit not all equally well. Note that any disequilibrium tends to be long-term unstable, and any fuel sitting around with a nearby oxidizer unburned is not an inherently stable situation, so we should not expect vast supplies of ready energy to be lying around on every planet. Indeed, the existence of this one is itself a biosignature of life, but it shouldn't be that rare either. There should be some sort of fuel lying around, not even including the one up in the sky that's presumably running all the life on that planet. In short, there's no real geological reason the stars should be silent because no one struck oil. Fossil fuels made our journey faster. They weren't the only road. If the cosmos is sitting on 13 billion years of chemistry, it's not short on biofuels. only on fire makers. Civilization collapse and the myth of running out. A common variant of the fossil fuel filter argues that civilizations burn through their easy energy, collapse, and can't climb back up. Their coal and oil spent, their machines rusty in ruins. It's a grim and tidy idea, but not a very convincing one. First, civilizations don't unlearn everything. A species that's mastered mining, metallurgy, and chemistry won't suddenly forget them. Most of what gets lost is the ability to manufacture something with a big supply chain and complexity, like a Roman aqueduct or a Saturn V rocket. The core knowledge is harder to lose. Even a collapsed society leaves books, ruins, and legends, seeds that make the next rise faster. The second industrial revolution we built from recycled scrap, not fossil seams. Second, we'd have options that didn't exist before. Hydropower, wind, and solar would still work even in a post-collapse world. Nuclear fuel remains abundant and is easier to use for power than to weaponize. Once you know fission, you don't need dinosaurs, just uranium, which every rocky planet seems to have plenty of. And most importantly, civilizations that reach the point of burning through fossil fuels must have already mastered energy conversion and storage. They would not need to start over from fire and stone, they'd start from whatever survived. A little ingenuity goes a long way when the ruins are full of batteries, wires, and solar panels. Collapse is not a filter, it's a setback. Plants that make it to industry are more likely to rebuild than fade away. Energy may run out, but curiosity does not, and that's the real spark that keeps civilization climbing. When we ask why advanced civilizations vanish or thrive, it often comes down to how they handle energy, curiosity, and knowledge. That same balance drives progress here at home, as what Imprint is all about. Imprint is a learning app built to make complex ideas simple, visual, and memorable, in a way that also helps build better learning habits. Each lesson takes only a few minutes and uses striking visuals and interactive design to help concepts really stay with you. You can explore courses on science, technology, finance, philosophy, decision-making, and leadership. Master big concepts in as little as 2 minutes per lesson. It's a smart way to turn a few spare minutes into meaningful learning and to keep feeding the curiosity that built our world. Try Imprint free for 7 days and get 25% off an annual subscription at imprintapp.com/IsaacArthur. Could you industrialize without fossil fuels? You don't need coal to invent industry, only the will to make things burn hotter, turn faster, and work longer. Fossil fuels made our industrial revolution fast, not possible. Energy is everywhere, if you know how to coax it out. Heat and power bootstraps. Before anyone found coal, charcoal ruled the forge. From India's wood steel to Europe's early bloomeries, civilization smelted iron with nothing but wood and patience. Forests limited throughput, but they regrew, a slow, renewable bridge to metallurgy. Windmills and water wheels followed, turning grains, looms, and hammers long before steam. Scale those up with better gearing and you have real industry. Add in geothermal vents or volcanic heat, and you've got smelters that never sleep. Even sunlight can serve. With mirrors, lenses, and steam, a desert world could leap straight to solar industry, skipping fossils entirely. Materials and chemistry without petroleum. Coal and oil made material chemistry convenient, not inevitable. As we said, early ironworking thrived on charcoal, and modern metallurgy can ditch coke altogether with hydrogen reduction or electric smelting. The Haber-Bosch process, essential for fertilizer, does not need natural gas. Its hydrogen can come from water via electrolysis. Plastics and solvents. Nature already provides cellulose, rubber, and shellac, and an electric civilization could refine carbon straight from the air. Chemistry depends on knowledge, not geology. Even aluminum, the metal of flight and modernity, owes its rise to hydropower, not hydrocarbons. Once you have current, the rest follows. Transport without oil. Mobility does not vanish without petroleum, it just evolves. Steam engines can run on wood instead of coal. Electrified rail can knit continents together, as efficient as a diesel line. Sailing ships, updated with composites and automation, can again move goods across oceans, on a nuclear fuel or even just really big sails. Synthetic fuels made from green hydrogen and captured carbon can power combustion engines and aircraft until better batteries arrive. Even airships might enjoy a renaissance, slower but steady and sustainable. Speed may define progress, but resilience sustains it. It may take them longer to get to a destination, but they should keep progressing, and they aren't on some peak oil or carbon dioxide deadline, so what's an extra century? A fossil-free industrial world might look different. Quieter skies, more rivers harnessed, more forests carefully managed, would not be trapped in the Dark Ages, which honestly were not actually that dark. With wind and water, chemistry and curiosity, any world can reach for the stars. Fossil fuels made the climb steeper for us, but it was not impossible without them. In the end, industry isn't just about what burns, it's about what moves. Nuclear as the universal backstop. Even if a world never strikes oil, uranium and thorium are waiting in rocks. They are not rare. Trace amounts are scattered throughout almost every planet's crust. Once a civilization masters mining and metallurgy, it's only a matter of time before someone isolates a strange heavy metal that warms itself. And remember, we had our first atomic pyros running before most Americans owned a car, or had running water and electricity, let alone most people worldwide. For that matter, we knew about copper-generated electricity when exposed to sunlight before Henry Ford built the first car. You can get some interesting alternate technology scenarios, and we explored some of them a year and a half back in our episode Anachronistic Technologies. Fundamentally, the path from curiosity to civilization's scale power is surprisingly short. A research reactor leads to a working fuel cycle. Breeder or molten salt designs follow, unlocking centuries of reliable energy. Fission is dense, compact, and weatherproof, a power source indifferent to wind, sunlight, or carbon. Once nuclear begins, the fossil fuel argument collapses. And nature got there first. 2 billion years ago, long before humans existed, the Oklo natural reactors in Gabon, Africa ran for hundreds of millennia. They went critical purely by chance, moderated by groundwater and fueled by ordinary uranium ore. That precedent tells us fission is not exotic, it's chemistry plus patience. We even explored its possible role in starting life on Earth in a Fermi Paradox episode a few months ago. With nuclear power, a civilization can make its own fuels, metals, and fertilizers, and build every renewable generator it could ever want. Uranium and thorium are the ultimate bootstraps, a near-universal fallback for any world that can dig. Space access without fossils. But what about getting to space? You need rocket fuel for that, right? Well, no. We've got some non-rocket options, but first and foremost, while the most common rocket fuel is basically kerosene made from fossil fuels, the best rocket fuel, at least in terms of specific impulse and keeping to chemistry, is liquid hydrogen and oxygen, which can be made from water and electricity. Hydrogen is a pain to store and to use, which is why it's not universal as a rocket fuel, but if we didn't have kerosene, it would easily fill that gap. Moreover, most of the work of leaving a planet is getting up to speed, and doing it quicker than gravity and friction can drag you down, and that can't be done without chemical fuels. Mass drivers and railguns can fling cargo skyward using electromagnetic acceleration. Indeed, this approach predates rockets in science fiction, so it's not like you have to invent rockets to come up with the idea of going to space. Some companies are even attempting to build spin launchers right now to fling objects into space with a giant slingshot. Beamed power from lasers or microwaves can energize launch craft remotely, turning power plants into spaceports. Even tethers and rotavators, those great orbital lassos and skyhooks, can transfer momentum directly, trading mass for altitude instead of fuel. And while I am uncertain if space elevators can be made to work on Earth, a planet with even slightly lower gravity probably can, and the same material needed for those, graphene, conveniently made from carbon, is also likely to be incredibly handy in making both superior batteries and superior hydrogen storage tanks. Rocket fuel is easier, but not the only way, and electric methods might turn out to be better. Beyond the atmosphere, electricity only becomes more dominant. Solar electric propulsion can move cargo efficiently between planets, while nuclear thermal rockets running on simple hydrogen can handle deep space missions without a drop of oil. Once you are in orbit, power is cheap, friction is low, and fuel is optional. Even propellant is negotiable in some cases. And fundamentally, anything can be made into a propellant. Civilizations that start industrializing in space might skip the entire fossil era altogether. Mining asteroids, refining metals, and producing propellant all rely on electricity, not diesel. The first colonies around other stars might never burn anything at all. Their power drawn from sunlight, fission, or fusion, their ships gliding on magnetism and patience. And oh yeah, let's not forget fusion. Until we have a commercially viable reactor, it is legitimate to wonder if it will ever work, but if it does, it rather neatly buries this whole problem. In short, a world is not locked to its surface just because there's no fossil fuels buried under that surface. Does depletion doom reboots? I think we've made a strong case at this point that industrialization and developing and continuing does not require fossil fuels, even if it can benefit from them. I am not instantly convinced that the lack of them would actually slow development at all, as a civilization might have gotten semiconductors sooner, jumped on solar and batteries, and skipped a lot of the other problems we've had from fossil fuel economies. Before we close out though, let's revisit the idea that if civilization collapses after burning through most of their easy fossil fuel energy, that they have a harder time climbing back up. The next cultural digs finds nothing and never reaches orbit again, a tragic cycle of rise, fall, and final failure. It is a tidy scenario, but assumes civilizations go extinct without learning. We did not stumble blindly through the fossil fuel age. We studied it, wrote about it, and left records that could survive far longer than coal seams. Even if our cities crumbled, if someone can dig up a fossil, they could probably dig up a turbine or solar panel too. I've also never really been clear why people think we'd lose such technology. A solar panel is not hard to understand, or even to make. Rather, it is hard to make it economically competitive with other power sources. Neither is it hard to modify engines or generators to run on wood. So you're never going to lose your civilization's usage of electricity after some apocalypse, and even if you did, you ought to regain it quickly and not even need buried and preserved versions. Moreover, it's not as though fossil fuels vanish after one pass. Oil and gas continuously seep through geology. Coal forms whenever forests rot under pressure, and methane comes from microbes that never went extinct. The reservoirs might dwindle, but the chemistry persists. And what's a few million years for a planet that will live for billions? Civilization is not a one-use match, it's a torch, and once you know how to make fire, you can always strike another spark. The same applies to rich metal veins, which is a common sibling or attachment to this concept. The ruins of civilization do not run out of metal. They recycle old wrecks, which is actually a lot cheaper and easier than digging out of the ground, especially if those richer seams are getting mined out. They will also refresh over geological timescales, and while those are immense to us, geological timescales are exactly what we have to contemplate for Fermi Paradox solutions. If it takes 100 million years to properly regenerate your metals and your coal, then you would still have several chances for that on Earth alone, and other planets probably have longer lifespans if they are around cooler stars than our own. And if the problem is energy scarcity rather than memory, nuclear power solves it neatly. One small cache of uranium ore could bootstrap an entire planetary grid. A post-collapse society that rediscovers fission would never again need fossil fuels. Their reboot would be nuclear. The Fermi Verdict. So, could the fossil fuel problem really be the answer to the Great Silence? Probably not. It's an elegant idea from a sci-fi story perspective, but it rests on a very human assumption that alien progress must follow our path through the same resources, in the same order. There's simply too many alternatives to it, and backup strategies if you run out of it. They all have to fail to prevent you from rising, or from rising back up. Nature offers far too many other routes. Charcoal and ethanol can light the first forges. Wind and water can power the first machines. Geothermal and solar can sustain whole civilizations indefinitely. Nuclear power can carry them beyond their atmosphere, and once in space, the sun itself becomes their endless energy source. The universe is not short on ways to turn heat into motion. Ultimately, the real fuel of civilization is not fossil fuels, it is willpower and creativity. It was before we struck oil, it will be long after we stop using it to run our cars on. When we look at the night sky, we are seeing energy in all its forms. Nuclear furnaces blazing in distant stars, fusion and gravity powering everything we know. The cosmos runs on transformation, and so do we. If life can arise on another world, it can learn to make heat, motion, and tools. Whether by wood, assuming they have trees, or wind, sunlight, or uranium, someone will find a way to turn nature's quiet forces into progress. Fossil fuels may have been our shortcut, but they're not the only key to civilization. So if the silence of the stars makes you wonder whether we are lucky or exceptional, remember, the universe does not hide its gifts. It's filled with energy, waiting for minds to find it. The question isn't whether others had coal or oil, it's whether they had the curiosity and determination to strive forward. And as long as curiosity exists, the fires of civilization can always be rekindled, and they will find other means to fuel their ambitions.